Hi everyone, in this lecture we'll be talking about the turning effect of a force, or also moments as we like to call them sometimes. So imagine you've been given these two objects, these two rods for example. Now on the first rod you have some weight acting downwards, and you also have the same force acting upwards. So this rod should be in equilibrium, right? Since the forces on it balance out. I'll write down a value as well. Let's say this is 10 newtons and this is also 10 newtons. Now on the second rod, or rod B, you have the same 10 newton force acting downwards, and on the other side you have this same 10 newton force acting upwards. This is 10 newtons and this is also 10 newtons. So the question is this object also in equilibrium? It's not, right? Since there are two conditions for equilibrium. The first is, our first condition for equilibrium is that the forces acting on a system should balance out. Now this condition, it's being met in both cases, right? You have a 10 newton force acting downwards in both cases, and you have a 10 newton force acting upwards. But our second system is clearly not in equilibrium, and this is because both these forces have turning effects as well. This brings us to our second condition, which is that the turning effects of these forces should also balance out. Now clearly this condition isn't being met in this case, and that's because this 10 newton force acting downwards gives you an anti-clockwise turning effect, and the 10 newton force acting upwards also gives you an anti-clockwise turning effect. So both of these add up. In our second condition for equilibrium, how we check if the turning effects are equal is by equating sum of clockwise moments with the sum of anti-clockwise moments, and these two should be equal. The formula for your turning effect is just force times the perpendicular distance. Force times perpendicular distance from the point from which you're taking the moment. So let's say you have this rod tilted at an angle, and there's a force acting on it. This force is acting downwards at some angle, and you need to find the moment or turning effect. Now in this case it's very simple. Since this is your distance d, this is your force F, and these two are already perpendicular. This is 90 degrees. So your moment would just be F times d. But what if instead of the force acting at an angle, you had the force acting vertically downwards? How would you find the perpendicular distance in this case? Well, one thing that you should keep in mind is, by the way, we're taking moments about this point, one thing you should keep in mind is that the perpendicular distance is always the shortest distance between your force and this pivot, or the turning point. Now a good practice to find the perpendicular distance is always extend the force vector until you can find this shortest distance. Now in this case you can see if I extended the force vector upwards, your distance would keep on increasing. But since I've extended it downwards, your distance, you can now find the shortest distance, or the perpendicular distance, which is this. If I kept on extending this, then again the distance would keep on increasing. So this is your perpendicular distance in this case. And how do we find this perpendicular distance? Well, that's simple enough. You have some angle, let's say theta, or instead of theta they can give you this angle phi, which is the angle between the force vector and our object. Let's call the original distance we had capital D, and you need to find small d, which is the perpendicular distance between your force and the point about which we're taking the moments. So in case you've been given theta, you can clearly see you can apply cosine in this case, right? Since d is adjacent to theta. So d would be equal to d cosine theta. In the second case, in case you've been given phi, again you can just apply simple trigonometry. D is opposite your angle, so D should be equal to D sine phi. In this case, we're simply resolving our distance vector into its horizontal component, which is the perpendicular distance between the force vector and your pivot. Now in most cases you'll have to rely on trigonometry, but there is a formula that we can take away from this. If let's assume this is your object and there's a force acting on this object at some angle. Let's call this angle phi. So, by the way, this is your force vector. This, we usually call this the lever arm, and the perpendicular distance, which I haven't labeled right now, is called the moment arm. So the formula that we can derive is the distance for the lever arm. Let's denote this by capital D. So the perpendicular distance in this case between your force vector and the pivot can be given by D sine phi. This will give you the perpendicular distance D. However, it's preferable if you make your right angle triangle and then identify the perpendicular distance. Since in this case you can see for yourself why the formula makes sense. You have a right angle triangle, you've been given an angle, and using this you can find the perpendicular distance. Since that's just a component of your lever arm that's opposite to this angle phi. And this perpendicular distance is your moment arm, by the way. I'll call this small d. And then you can just apply the formula F times small d, and this will give you the turning effect or the moment about point P. So if you want to use this formula, there are some conditions that you need to keep in mind. The first being that the angle that you're using should be between your force vector and the lever arm. And the second is that you should always take the acute angle or less than 90 degrees. Since in this case, this angle theta is also an angle between your force vector and the lever arm. but the distance it gives you is not the perpendicular distance. And as for when you're identifying this lever arm, the only thing that you should keep in mind is that this is the distance between your pivot and the point at which the force is acting. If you had an oddly shaped object, something like this, and you had a force vector acting on this object, then it's easy, and by the way, you're taking moments about this pivot point, so it's easy to assume that this is your lever arm. But if you remember the definition, it's the distance between your pivot and the point at which the force is acting. So this will actually be your lever arm. Taking the moment arm should be simple enough. You just extend the force vector upwards until you get a right angle triangle. This, which would mean this distance, is your moment arm. And that's it from my end. I'll see you guys in the next lecture where we'll be solving some examples.